5C, conditional probability and the multiplication rule. So conditional probability is a probability computed when you have a knowledge of some additional information. So basically it means you already know something before you determine the probability. Therefore, your judgment of what the probability is conditional upon that prior knowledge. Thus far, we've dealt with unconditional probability when it's computed without additional knowledge or additional information. So basically, conditional probability, we already know something about it. Unconditional probability, we don't. When we're writing conditional probability, we write it as P, parenthesis, A, vertical line, B, close parenthesis. So that's a vertical line. And that vertical line stands for given that. So we're looking for the probability that event A occurs given that event B has already occurred. So we're making a judgment based on some prior knowledge. Usually what we mean by that is maybe I'm looking at the number of people who wear glasses out of a full class. So let's say we have 11 people wearing glasses and there are 28 people in the class. Then my probability of randomly selecting a person wearing glasses is 11 over 28. Now let's add a little more information. This is an unconditional probability. We know how many people have glasses out of how many people in the class. The probability that someone wears glasses is 11 out of 28. Now I add this additional piece of information, or additional pieces of information, we'll say that. What if I say there are 19 females in the class, and of those females, 4 are wearing glasses? Right, so now I've got this additional information. So if I want to find the probability that someone's wearing glasses, that I select someone wearing glasses, given that they are a female, now I can base the probability of selecting someone who's wearing glasses on the fact that I know that it's a female that gets selected. In that case, there are only 4 females wearing glasses out of the 19 females in the class. And I shouldn't have to plug this in my calculator to show you what those probabilities are, to show you that it's different. You got 11 out of 28, that's a little over a third, and you've got 4 out of 19, that's less than a quarter. So obviously 2 different probabilities, but this is an unconditional probability. We just want to know the probability that we select someone who's wearing glasses. This is a conditional probability. We want to know the probability that we select someone who's wearing glasses given that we selected a female. We have that additional information which moved us from 11 out of 28 to 4 out of 19. And if you look at what I did here, what happened on the top? We took 4, which is females with glasses. That's both female and glasses occurring at the same time. On the bottom ended up being females. So conditional probability that A occurs given that B has already occurred, or given that we know that B occurs, is equal to the probability that A and B occur over the probability that B occurs. And that's just what we did here. We said, look, the probability of selecting someone who's wearing glasses, given that we know it's a female, is 4, the number of people who are female and wearing glasses, over 19, the number of people who are female. Basically, we're saying, okay, let's localize it to the information we know. Our number of possibilities, or our total possibilities, are just whatever that given piece of information is, given B. So we've localized it down to that, and then we're looking for those items that are part of both A and B. So let's play with this a little bit and put a contingency table in place. So we're going to put a contingency table here. So let's say we have sandals and sneakers, prefer to walk places or ride places. That gives me a lot of flexibility there, whether it's ride in a car, ride a bicycle, ride on a skateboard, whatever the case may be, right? So people who wear sandals, people who wear sneakers, people who walk, people who ride, or prefer to walk, prefer to ride. So I have 17 people who wear sandals who prefer to walk. I have 36 people who wear sneakers who prefer to walk. I have 21 people wearing sandals who prefer to ride, and 29 people wearing sneakers who prefer to ride. So this is a good opportunity for us to practice working with contingency tables. So let's put those summations together. Total number of people wearing sandals, 17 plus 21, 38. Total number of people wearing sneakers, 36 plus 29, 65. Total number of people who prefer to walk, 17 plus 36, 53. Total number of people who prefer to ride, 21 plus 29, 50. And then remember that last little bit here. How many people total? 53 plus 50 is 103. That was a really sloppy sigma. Or 38 plus 65, 103. So now that we've got that, we can put these together. Well, let's see. What is the probability that we randomly select a person who prefers to walk, given that we know they wear sneakers? I'm just going to do SN for sneakers, SA for sandal, W for walk, R for ride, just to make my life easier. Well, what do I need to know? According to our formula for computing conditional probability, I need to know the probability that we find of selecting someone who walks and wears sneakers. So that's 36 over 103. Right? The probability that of W and SN, that's here, that's where they both occur, over the probability that whatever the given is, that they wear sneakers. How many people wear sneakers? 65 over 103. So now I have to do a little bit of a division there. Luckily, 36 over 103 divided by 65 over 103. If I multiply the top and bottom by 103, I come down to 36 over 65. And I look at that and I see that that's not going to simplify anymore. So the probability that we randomly select a person who prefers to walk, given that they're wearing sneakers, is 36 over 65. Which makes sense if we look at it. We know that they wear sneakers. There are 65 people who are wearing sneakers. And we want the probability that they walk. There are 36 people who walk out of those 65. So 36 over 65. Now I know you're looking at this and going, but Mr. Davis, why would I want to do all this when I can just pull that straight out of the contingency table? Well, that's because that contingency table is not always there for us. So let's look at an example where we don't have that. What if we know the probability of passing this class is 0.71? The probability that a student has has a TI calculator is 0.84. The probability that a student passes and has a TI calculator. Now remember, don't confuse and or. Passes and has a TI calculator. Both of those things have to occur. Passes or has a TI calculator, one or the other occurs and we're happy. If they both occur, we're still happy. So we want the probability that someone passes and has a TI calculator. So the probability that someone passes and has a TI calculator, or you could say someone who passes who has a TI calculator, is 0.58. Now remember, this isn't the probability that someone who has a TI calculator passes. This is the probability that someone passes and has a TI calculator. Both of those things occur. I want to find the probability that someone has a TI calculator given that they pass the class. So we know they passed the class, we want to find the probability that they have a TI calculator given that they passed the class. We know the probability that they have a TI calculator is 0.84. We know the probability that they pass is 0.71. We know the probability that someone has a TI calculator and passes the class is 0.58. What's the probability that someone has a TI calculator if they pass the class? So we're looking for the probability that both of these things occur, 0.58, over the probability that the given thing has occurred, which is passing, 0.71. Let me grab my calculator quick, which is not a TI. So we got 0.58 divided by 0.71, which gives me approximately 0.82. So the probability that someone has a TI calculator given that they pass the class is 0.82. So 82% of the people who pass the class have a TI calculator. Now I just want to put a disclaimer in here. Having a TI calculator or having some other calculator is not indicative of what you're going to get in this class. So if you have a Casio calculator, it's okay. There are groups that you can go and join to, kind of like AA. So you can say, hi, I'm Bob, and I have a Casio calculator. And people will commiserate with you. So here we go. So conditional probability, the probability that both things occur over the probability that the given part occurs. That's the biggest thing to remember. The given part is what goes in the denominator. Probability they both occur, that's not the sum of the probabilities. That's not 0.71 plus 0.84. It's the probability they both occur. Now, you may be looking at this and going, well, how did you come out with the probability that they pass? How did you come out with the probability of TI? How did you come out with the probability of passing TI? I don't know where that number came from. They came from my head. Random numbers that I pulled out. Okay? You can't calculate these just out of the blue. This is information that would be given to you. The only way you could calculate it is you'd have to have a whole bunch of people and see how many passed and how many failed. You'd have to see how many have TI calculators, how many don't. You'd have to then see how many that passed have TI calculators. Okay, so just keep that in mind. These were given, we then used that to determine the probability that someone has a TI given that they pass. So conditional probability. Now, let's move on to the multiplication rule, or the general multiplication rule. So the general multiplication rule. General multiplication rule comes from conditional probability. Remember, conditional probability was the probability that A occurs given that B has occurred is equal to the probability that A and B occurs over the probability that B occurs. Okay? That was conditional probability. General multiplication rule tells us that the probability that both A and B occurs is equal to, well, solve this for probability of A and B. The probability that event B occurs multiplied by the probability that event A occurs given that B has occurred. So that's why it's called the general multiplication rule. We're multiplying the probability that event B occurs by the probability that event A occurs given that event B has occurred. Multiplication rule. So if you have two, I don't want to say events, but if you have two trials that are happening here, then you can find the probability that both A and B occurs given a multiplication equation here. Probability of B times probability of A given B. Well, let's look at an example of this and what's going on here. Let's say I want to pull an ace from a deck of cards. The probability of pulling an ace from a deck of cards is equal to 4 out of 52 or 1 out of 13. Right? That's the probability of pulling an ace from a deck of cards. So 52 cards, 4 aces, 4 out of 52 or 1 over 13. What's the probability of pulling a king from a deck of cards given that we just pulled an ace? So we're going to do this, well, I'm going to say without replacement two terms that you need to know: with replacement, without replacement. With replacement means the item goes back in, so it's selectable again. Without replacement means it does not. So if I want to know what the probability of me pulling a king is, given that I pulled an ace prior to that, then that probability, well, how many kings are there in the deck? There are 4. But if I've already pulled an ace out of the deck, then I'm now down to only 51 cards. So 4 over 51. So now I want to know what's the probability that I pull an ace followed by a king. What's the probability I pull an ace followed by a king? So I pull an ace and a king. That both of those events occur. It's equal to the probability that I pull an ace, which is 1 over 13, times the probability that I pull a king, given that I pull an ace, 4 over 51, which is equal to 4 over, what's 13 times 51? 663, or approximately 0.006. So approximately 0.006. So the probability that I pull a king followed by an ace. Sorry, an ace followed by a king. Make sure we answer the correct question. But it just says, what's the probability of the first event occurring multiplied by the probability the second event occurs? Now, if we're looking at something like that, sometimes we run into the things of this. What if I flip a coin and roll a die? So I flip a coin and I roll a die. I want to know what's the probability that I get heads and a 6. So I'm doing two things, right? I'm flipping a coin, then I'm rolling a die. I want to know what's the probability that I get heads and a 6. Well, general multiplication rule says, what's the probability that I get heads? So I'm just going to write this out first. Probability that I get heads multiplied by the probability that I get a 6, given that I've got heads. Okay, that's what our general multiplication rule says. The probability that I get heads is 1 out of 2. The probability that I get 6, given that I got head, well, actually, does the probability of getting a 6 change whether I got heads or tails? No, it doesn't, right? So what's the probability of getting a 6? 1 out of 6. So what's the probability that I get a heads and a 6? 1/12. But we just noticed something here. The probability of getting a 6, given that I got heads, is equal to the probability of getting 6, period. Right? This conditional probability is equal to just plain the probability of getting a 6, because the two events are independent. They're independent. The one does not depend on the other. So the probability does not change. If you have independent events, then the probability that event A occurs given that B has occurred is equal to the probability that event A occurs. So we have independent events because the probability of rolling a 6 is the same whether I got heads or whether I don't know if I've got heads. So that additional knowledge doesn't change the probability. Those are called independent events. Well, what does that do to our general multiplication rule? Well, now we get a specific case of the multiplication rule. For independent events, the probability that event A and B occur is equal to the probability that event A occurs multiplied by the probability that event B occurs. We don't have to do the conditional because if the events are independent, then the probability of this event occurring is equal to the probability of that occurring given that that has happened. So those are considered to be independent events, and it has no effect on it, which allows us to actually extend this, and we can say the probability that A and B and C and D and E and F occurs is equal to the probability that event A occurs multiplied by the probability that event B occurs multiplied by the probability that event C occurs, that event D occurs, that event E occurs, that event F occurs, right? We can multiply as many times as we want. So let's flip a coin, but let's flip it over and over and over again. So if I flip a coin 5 times, what is the probability that I get 5 heads? So I flip it 5 times, I want to know the probability that I get 5 heads, or that I get a head each time. Well, the multiplication rule, first of all, we look at it and say, well, every time I flip a coin, it's an independent event. Doesn't matter what happened before, I still have a probability of 1/2 of getting heads. So if I flip a coin 5 times, what's the probability of me getting 5 heads? Probability of getting heads the first time is 1/2. Of getting heads the second time is 1/2. Of getting the third time is 1/2. Of getting the fourth time is 1/2. Of getting the fifth time is 1/2. So the probability of getting heads 5 times in a row, 2, 4, 8, 16, 32, is 1/32, or just over 0.03. So that's the probability of getting heads. And they're independent events, so all I have to do is multiply through, which makes life a little bit easier. Okay? Now we talked about replacement and without replacement. In this case, this would be considered with replacement, because every time I flip that coin, I have both options available to me. Without replacement would mean that a side of the coin disappears each time. So when you're dealing with flipping coins, rolling dice, those are obviously with replacement. You automatically have to have that side of the coin still available for the next toss. You still have to have that side of the die available. It's not like you roll a 6-sided die and then the next time there's only 5 sides there. Okay? So that would be with replacement. It goes back in. As opposed to when dealing with a deck of cards, that could easily, you could do without replacement, that the card goes out and it stays off to the side. Or if you're selecting people to be part of a sample, then that would be without replacement, because once you've selected someone, you're not going to select them again to be a second person involved in the sample. So that's part of what goes into this to make it so that we can deal with independent versus dependent and deal with replacement or without replacement. Now, last thing, well, actually, let me do a quick thing here just to show the difference in this. What if I ask the question, what's the probability that I select 4 aces in a row from a deck? Now, the first question we have to ask is it with replacement or without replacement? So I'm going to randomly draw 4 cards, and I want to know what's the probability that all 4 of those will be aces. Well, it's dependent on whether you're dealing with replacement or without replacement. So let's say we do it with replacement. So with replacement, the probability of selecting an ace the first time, remember there are 4 aces in the deck, and there are 52 cards in the deck, that would be 4 over 52. The probability of selecting the second card as an ace, this is with replacement, so that card went back into the deck, so I still have 4 aces out of 52. The third ace, I still have 4 aces out of 52. The last one, I still have 4 aces out of 52. So 4 times 4, 16. 16 times 16, 256. 52 to the 4th. 7, 3, 1, 1, 6, 1, 6. So 256 over 7,311,616. So 256 divided into that gives me a probability of 0.000035 approximately. So the probability of selecting 4 aces from a deck of cards with replacement is 0.000035. Not a very likely occurrence. Now let's do it without replacement and see what happens. Well, the first one I showed a poll, there are 4 aces out of 52 cards. But now because we're not replacing that card, there are only 3 left out of 51 cards. And then because we're not replacing that card, there's only 2 left out of 50 cards. And then since we're not replacing that one, there's only 1 left out of 49 cards. So now I have 4 times 3 times 2 times 1, so 24. Over 52 times 51 times 50 times 49. So that's 6497400. So that's 6,497,400. And if I divide, I get 0.000037. Notice there's 5 zeros here, there were 4 zeros there. So basically, I'm about 10 times more likely to pull 4 aces in a row if I have the ability to put the ace back in the deck each time than I am to pull out 4 aces in a row if I'm not able to put it back in. Because here, really, each time I have the possibility of pulling one of 4 aces, here I'm pulling the 4 aces in sequence and then I have none left. I get done with this, I still have 4 aces in the deck. I can do it as many times as I want. So that's with replacement versus without replacement. And we see that generally you have a higher probability if the thing can go back in being replaced. Okay, so final thing I want to do with this is this is pretty cool, probability that we get 4 aces. But let's go on to a question that many times confuses people and throws them off, is let's say I pick 5 cards from the deck. I want to know the probability that at least one is an ace. So I pull 5 cards from the deck at random. I want to know the probability that at least one is an ace, and we're going to do this with replacement. Okay, so with replacement. So it's going back in here. So the probability that at least one is an ace. Okay, well, what do we need to do then? We need to find, that's equal to the probability that I get 1 ace plus the probability that I get 2 aces plus the probability that I get 3 aces plus the probability that I get 4 aces plus the probability that I get 5 aces. For consistency's sake, okay? Right? The probability that I get at least 1 ace, that's the probability that I get 1 ace, plus the probability I get 2 aces, plus the probability I get 3 aces, plus the probability I get 4 aces, plus the probability I get 5 aces. Well, worse than that, that already looks like I have to do a bit of work. But we also have to realize that there are numerous ways that I can get 1 ace. Exactly 1 ace. Start with an ace, the other 4 cards are not aces. Start with a card that's not an ace, get an ace, 3 cards that aren't. 2 cards that aren't, an ace, 2 cards that aren't. 3 cards that aren't, an ace, a card that isn't. 4 cards that aren't, an ace. So there are 5 ways that I could end up with 1 ace. And I need to get all the probabilities of those. So that's 5 probabilities, included this probability here. 2 aces, well now I've got to look at all the different ways that I can end up with 2 aces, which there are more than 5. They keep coming. All the ways I could end up with 3 aces, all the ways I could end up with 4 aces, all the ways I could, which is only one way I could end up with all aces, right? They're all aces. So that's a lot of calculations. What we're going to do is we're going to bring in the rule of complements. Remember complement? It was the opposite. So if I know the probability that something occurs, then I can subtract that probability of from 1, and that gives me the probability that it does not occur. Well, looking at this, I want the probability that at least 1 is an ace. What is the complement of that? The complement of that is the probability that there are no aces. Right? If this is that there's 1, 2, 3, 4, or 5, then the only other option is that there are no aces. That's really easy for me to calculate. I know the probability of selecting an ace is 1 out of 13. We already covered that, right? 4 out of 52 or 1 out of 13. Well, if I want to find the probability that I don't get any aces, then that's the probability, that's equal to the probability that I don't get an ace times the probability that I don't get an ace times the probability that I don't get an ace times the probability that I don't get an ace times the probability that I don't get an ace. Right? Well, if the probability that I select an ace is 1 out of 13, the probability of not an ace is equal to 12 over 13. It's what's left over. So if I want to find the probability that I don't get any aces, that's 12 over 13 times 12 over 13 times 12 over 13 times 12 over 13 times 12 over 13. Which is 248,832 over 371,293, approximately 0.67. So the probability that I don't get any aces is 0.67. So therefore the probability that I get, I'm going to do greater than or equal to 1 ace just to save myself writing. Okay, that's at least 1 ace, is equal to 1 minus 0.67 or 0.33. So here, probability they got at least 1 ace, all these probabilities that I have to calculate. Here I said, well, let's use the complement of that, which is the probability that I don't get any aces. I do one calculation, and then I subtract that from 1 to find the probability that I get at least 1. So a really handy method to be able to determine the probability that something occurs at least once by calculating the probability that it does not occur ever and subtracting it from 1. So now we've got conditional probability, multiplication rule, and using complements to find the probability that something occurs at least once.